Passar para inglês, que vai ser a língua das palestras de hoje, mas antes eu quero dar as boas-vindas a todas e todos que vêm de várias partes do Rio de Janeiro para ver o COLMEA de hoje. Nós vamos ter duas palestras, da Andressa Cerqueira, que eu já vou apresentar, e do Gabo Lugosi, que está ali sentado. Entre as duas tem um coffee break, e também no final de tudo tem um café e uns biscoitos para a gente bater papo. Deixa eu começar, então, apresentando a professora Andressa Cerqueira. Ela é professora da Universidade Federal de São Carlos. A trajetória acadêmica da Andressa foi na USP, começando no departamento de matemática, depois indo para a pós-graduação em estatística, onde ela se doutorou sob a orientação da Florence Leonardi, que muitos de vocês conhecem. Durante o doutorado, ela passou um período na França, em Toulouse, fazendo um sanduíche com a Eliane Gaivier. Depois, ela fez um pós-doutorado em Campinas, não é isso?
Isso.
E com também um período fora com a professora Lisa Levina, na Universidade de Michigan. E a Andressa vai falar agora do trabalho de pesquisa que eu, por acaso estava na banca de doutorado dela, né, essas coisas de ser velho, que eu sei que é uma linha de pesquisa, quer dizer, relacionada a uma linha de pesquisa que ela já desenvolve há muitos anos, né, de detecção de comunidades, modelos estocásticos de blocos. E, bom, sem mais delongas, deixar a palestrante falar.
Thank you, Roberto. So now we can change to English, right?
Yeah, it's all English for now.
Okay. So good afternoon, everyone. So thank you, Roberto, for inviting me here to be here today. Actually, it's a pleasure to be here in IMPA because, fun fact about IMPA, the first talk that I gave in my entire life was here, exactly in this room, but it was in that corner because I remember very well. And then I was an undergrad student during that time. So for me, it's really nice to be here again in IMPA. So today, I'm going to talk about community detection in weighted networks. But before we start talking about community detection, I would like to give some ideas why we are interested to study networks. So here I have this structure here that's a network where I have the objects of study is the nodes of the network. Let me just see. Yeah, there's a pointer. So the nodes of this graph here is the objects that I want to study. And then connection between them, the interaction between them, I represented by the edges of this network here. So I don't know if you can recognize what is this. So we have the shape of Brazil here. So this is the air transportation network in Brazil. So nodes here are airports, and the edges means that if we have at least one flight between two airports. Right? So no, just ignore the self loops because I forgot to remove them. Because sometimes, because sometimes that happens when you collect the data. That happens because sometimes the plane just took off and then they need to return. Don't know why, but I forgot to remove the self loops. But I use this picture all the time. Yes, probably one problem here. So we are interested to analyze this kind of structure. So from a statistical point of view, we need to use different methods. The methods that we are not used to use to analyze, for example, a vector of data. So since here I have this object, this structure, I need to develop and I need to study different methods to analyze this kind of networks. And what we can do. So here I put everything together so we can analyze this network from a statistics or from a probabilistic point of view. So from statistics, what we can do is define a statistical model to describe this data, this network. And then since you have a statistical model, what kind of questions we have? For example, I can, since I have a statistical model, I have parameters for that model, so I would like to infer these parameters of this model. Or sometimes, if I have a collection of networks, I would like to test some hypotheses about this network. So I can create hypothesis tests to test something about this network. For a statistical point of view, we can try to cluster the nodes of this graph. This is what we are going to talk today, what I'm going to talk today. So I can try to divide this network in groups. So I will create cluster of nodes in this network. So I'm just using the word clustering here because it's very common in statistics, but in the network science, we call it different. Or, if you want, you can define a probabilistic model. I just write these two models different because sometimes in statistical model, we can also describe a model using covariates, for example. So sometimes I can add covariates in the nodes of the graph, and then I have a more complex model to describe that data. From the probabilistic point of view, we can define a model, and sometimes we add some kind of dynamics. So sometimes we can have a stochastic process on the graph, or a stochastic process that generates, I don't know, graph that's evolving on time. This is an example that I have on my mind. And then from the probabilistic point of view, what we want to study is asymptotic properties of that model. What happens when the network grows? And then I study theoretically properties of that model. Or some dynamics that we define on networks. So I usually, here I describe the problems that I work on. So today I'm going to talk more from a statistical point of view, right? So here's just an overview for you to get on mind that we have a lot of questions related to network data. So I bring this example here that is very famous example in networks. So this is the most cited data set when we work with community detection or when we work with networks. So I just bring this example today has a motivation to explain why we search communities in networks. So this is the data from the Zachary's Karate Club. One point here that's interesting, because all the time I thought that the owner of the Karate Club was Zachary. But no, Zachary is the researcher that published the paper that contains the data from this Karate Club. So there is no Zachary in the data. So he's just the author of the paper. And in this network, we have 34 members of a Karate Club. So the members here, the individuals, are the nodes of the graph. And we have here the interaction between them. So the interaction here means that these two individuals are friends outside the Karate Club. If they have a relationship, not a friendship outside the Karate Club. And what's interesting about this data is that we have two members here, this one and this one. I don't remember exactly who is the guy who takes care of the club, and the other one is the professor. I don't remember the order. But they fight, and then they kind of split the relationship in the Karate Club. Because we have, since they fight, one of them open a new Karate Club or whatever. And then when we look at this relationship network, we can see these two communities that arise. So we can see here that we have more, here in the orange community, we have the individuals that are friends with this guy, and in blue community, we have the individuals that are friends with this one. And then you can see that since they fight, there is not a relationship between the two groups. I mean, only a few, for example, this guy and this guy, but we have more connections between the groups. So this network becomes very popular because now we have a question that's natural in some way to have networks with community, with a community structure in the data. So what we want to do is to recover this community structure that sometimes we can't observe. Actually, we never observe. In this example, it's well studied because we know the true communities, so we always, the researchers always use this example to certificate that their method is working well. So this is why this data is very used. But so this is why we are interested to analyze or just trying to describe, create models for networks that have community structure in the data, right? Okay. So this is what we call community detection. So here I have a network with 3 communities, and communities for us means that I have a group of nodes such that I have more connections between the nodes that are in the same group. So if you look at this picture here, I have a lot of edges inside the groups than between groups. I have less edges between groups here. So this is what we define as a community. And okay, but I need to try to represent this figure in such a way that I can handle with the data, and then I can try to develop some method to recover communities or do some inference about this network. So what we use is the adjacency matrix of this graph. You want to? Mm-hmm. No, but I have a lot of connections. Yeah?
So do you require that someone has more neighbors to be inside the community, you have more neighbors in your own community than outside the total? Or just more than that one than each of the others? Is it supposed to be a precise definition, or is this just a...
No, it's not a precise definition. It's just a way to explain what's a community. Yeah. So to represent this graph here, I use the adjacency matrix of the graph. Here is not exactly a matrix. I just put a figure here to represent the adjacency matrix. But let me explain what's that. It's just the adjacency matrix of the graph. So what I have in the lines, the columns, are the nodes of the graph. And then the black dot here means that I have a connection between a pair of vertices. So that means that I have 1 in this matrix, the entry 1 in this matrix. And the white dots here means that I don't have an edge between pair of vertices. That means 0 when I look at the adjacency matrix. So the adjacency matrix is just a matrix with zeros and ones, when 1 means that I have a connection. So this is just a figure to see what happens. Here, I ordered the nodes of this network. So here, in the first lines, I put all the nodes that belongs to the first community. Then I put here all the nodes that belongs to the second, and then all the nodes that belongs to the third. And when I do this, I can see this kind of block structure in the network, because as I said, I have more connections here between nodes in the same group than between nodes in different groups. So it's not... I don't have all the connections here, so we can see that here we have these white dots here. So it means that it's not fully connected graph in one group. But we can see this kind of block structure when I look at this adjacency matrix. But what happens in real life is that someone comes to me with a network and gave me what? The adjacency matrix, right? And then when I look at the adjacency matrix, it's something like this. Right? It's the same matrix. I just reordered the nodes because I don't know the communities. And then I say, okay, let me plot the graph. Let me see the graph. And when I do so, I have something like this. Okay? It's the same graph that I showed you before. It's the same one. But this is real life. This is what we have. We have this gray picture, a matrix with a lot of 0 ones, and I would like to detect the communities of the graph. Right? So this is the problem that we have. So this is what we call community detection. So I just want to go from this gray picture to this very nice and colored picture here. Right? So this is what we are going to talk today. So, okay, to do community detection, what statisticians do is just to define a generated model to describe the data in such a way that this generated model describes the community, and then I would like to infer some parameters related with the community and say, okay, now I recover the communities. So let's see what we do. So, oops, sorry. So we have here this very famous paper that describes what is the stochastic block model. That's the most, probably the most famous model to describe networks with communities. So, okay, let's see what, how to construct this model here. We start with latent random variables. That means that these are the variables that we do not observe. There's the variables that they are in the model, but I can't observe these variables. So these are the variables, since it's the variables that I cannot observe, are the variables that describe the community. So to describe the community, I'm using C here for community. So suppose that I have a graph with n vertices. So I have here C1, C2, Cn, describing the community of each vertex. So C1 describes the community of vertex 1, C2 the community of vertex 2, and so on. So the communities here, it's a random variables to us. So it's, we give a community to a vertex randomly, and we define that these variables are ID, they are independent, identically distributed, and we have that for node I, the probability of node I belongs to community A is given by PA. Okay, that I don't know. It's just a parameter of the model. And here I have a total of k communities. So in the previous example, k is equals to 3. I have only 3 communities. So here I'm fixing k, capital K, for the number of communities. So I have this vector here of the probabilities for each community that should sum 1. And k sometimes is defined as no, but we are going to talk more about this later. After I have this distribution for the communities, I now can define the observed variables of my model. So what we observe, remember from that gray picture, the only thing that I observe are the edges. So I'm going to give a distribution for the edges. Since edges is just 0, 1 for us, 1, that means that the edge is in the graph is 0, there's no edge between a pair of nodes in the graph. I can define each entry of the adjacency matrix has a Bernoulli random variable, right? So what we have here is that conditional on the communities of node I and j, so conditional that node I belongs to community A and node J belongs to community B, I have that the entry AG of the adjacency matrix follow a Bernoulli random variable such that the parameter here, the probability to have a 1, depends on the communities of the nodes. So depends on A and B, right? So for each possible pair of communities, I have a probability associated with n. Since I have k communities in total, I can describe all these probabilities by a symmetric matrix that I call K, that I call P. That's K by K matrix. So here I have K times K parameters in this matrix. And for this vector here, I have K parameters, or K minus 1, because 1 we always get from the other ones. So these are the parameters of the model. Okay, this is the stochastic block model. And from a statistical point of view, the questions that the problems that we, oops, spoiler, the problems that we have for this model basically are 3 that are listed here. So remember, we only observe the adjacency matrix, we only have A. So the first question is how to estimate the Cs, right? So how I can estimate the vector of the communities associated to each node. So this is what we call community detection that I explained before. The second problem is to infer the parameters of the model. The parameters are the vector pi and the matrix P. This problem here actually is not very well studied because since I know the communities, it's not that difficult to estimate the parameters. We just use the maximum likelihood, if I know the communities. So basically what we do is just do the step 1, estimate the communities, and then I know how is how to infer the parameters. So basically we don't study a lot the second problem here. And also there are some methods that solve 1 and 2 together. And this is the method that I'm going to show today, so this is what we get. And then third one, so to solve 1 and 2, we need to assume that K is known, because I need to assume that I know how many communities I have in the network, right? So this third problem, that should be actually the first one, is to estimate how many communities I have. So in community detection, we just assume, okay, let's assume that there is 3 communities, and then I infer the community of each node. So, so this is why I think that this should be 1 sometimes, but there's few works about estimating number of communities. Actually, this is what I studied during my PhD, but it's not what I'm going to talk to you today. So this is what we call a model selection problem, because when I change K, I change the number of the parameters that I have, right? Because the number of parameters depends on K. So I'm changing the complexity of the model, because more parameters, if I have a lot of parameters, I have a model that's very complex. So in statistics, we call this kind of problem to model selection. Okay, so these are the 3 problems that we usually are interesting to when we work with networks. So today I'm going to talk about the first one. So for the stochastic block model, there are a lot of methods to do community detection. I mean, so many that I didn't make a list here because I know that it will be unfair, because probably I will forget some paper, so I didn't put a list here. But just to give an idea for you, we can use methods based on the likelihood of the model. So from a statistical point of view, we write the likelihood of the model and try looking at this likelihood to estimate the communities. Or for example, if you're a Bayesian statistician, you can define some prior on the parameters, use the likelihood, and then estimate the communities. There are also some spectral methods that instead of use the likelihood, since we have a matrix, an adjacency matrix, you look at the spectrum of this matrix. So you look at the set of eigenvectors and eigenvalues, and then you define a method to estimate communities based on that. It's really nice theory. So there are a lot of methods based on the spectrum of the graph. There are also methods based on modularity of the networks or other properties of the network. So there are a lot of methods. But what I'm going to talk today that is different in some sense is that this model that I described here, the stochastic block model, only consider what we call binary networks. So it's networks where the adjacency matrix is just 0, 1. The only thing that matters is that if there is or there is not an edge in the network. Okay, but let's see that sometimes when we look some real data, sometimes we have more information that we can take in an account, and maybe binary networks is not the better way to describe these networks. So here's an example when we analyze brain networks. So suppose that we have individuals doing some task. Here's just watching a video, but doesn't matter. This is not the data that I'm going to talk today. I just bring this figure because it's really, really nice, right? So we have individuals doing something, and then we record some brain, we record the brain activity of these individuals. So here, the recorder was EEG. So we put electrodes in the head, now the scalp of the individuals, and then we collect the electrical activity of the brain. When you look in the data, we have this time series of the activity of the brain. What we do if you want to analyze this data from using networks, what we do is just calculate some correlation between these two time series. And when I have this correlation, I can construct this network here with the this matrix here with the correlation between two pair of electrodes, right? And what we do actually is just try to define a threshold to transform this matrix here that doesn't have 0, 1 entries to a matrix with 0, 1 entries to be represented by a graph, and then using this graph, we use like stochastic block models or other models for binary graphs to do whatever we want, for example, community detection or test hypothesis, other things. So what's interesting here is that we have this matrix here, which entries are not 0, 1, that contains a lot of information of the data. And then put a threshold here, we are losing this information, right? So instead of doing that, what we can try to do is say, okay, I will consider that I have the edge between pair of nodes, but I have more information about this edge. I know the strength of this connection, right? And the strength of this connection can be, for example, correlation in this scenario here, right? And this is why I'm going to talk about weighted networks. So in weighted networks, we have the information that I have an edge, and also the information of how strong is this edge in the network, the strength of this edge in the network. So this is just to give a motivation why we are interested in weighted networks. So for example, when I started this talk, I talked about this air transportation network, this Brazilian air transportation network, that can be modeled as a weighted network, where instead of using just the information that I have at least one flight between two airports, I can count how many flights I have or how many passengers I have, right? So this is also a weighted network. For example, in a friendship network, I can measure, I don't know why, but how, but they do, how is my, I don't know how to say, but how is my, how strong is my relationship with that person? Okay, we can try to do that, and then I have a weighted network. Actually, if we think, I think it's more natural to have network with 8 than network that's just 0, 1. I don't know. For me, for example, in the data that I work on, that happens. So why not use, instead of use a binary network where we are losing information, use a weighted one, right? So this is, so what I'm going to present now is a model that's, the idea comes from the stochastic block model, but now we put weights on the edges. So we have the same setting as before. In the stochastic block model, we have the latent variables. This is the same, right? But now, when I define the adjacency matrix, I will define now an edge-weighted network, an edge-weighted matrix. So the entries of this matrix here will be real. I will explain why. And we define here that the entry I and j, so the strength of the connection between the pair of nodes I and j, given the communities, is described by a Gaussian, a normal distribution, with mean and variance that depends on the community of the nodes. So now, instead of having only one parameter, that was the p that I described before, now I have two parameters, the mean and the variance. And the diagonal, we always set as 0. It was the same for the stochastic block model, just forgot to put in the slide. One thing that was important that I forgot to say is that conditional on C, all these entries are independent, right? In the stochastic block model is the same. So we have independence, conditional independence of these variables, conditional on the communities. So now I have B, a matrix of means. So now I have k times k means here, and a matrix of variances, k times k as well. And as before, W is a symmetric matrix. So, okay, the first question is why Gaussian, right? This is why we choose to use Gaussian here because the data that we have, the data that I'm going to present today, we have the information about fMRI. It's the same scenario as before, but instead of have EEG signal here, we have fMRI and signal. And when what is we use it do in this area is when we calculate the correlation between the time series, we apply a Fisher transform on these correlations. And then after applying this Fisher transform, the result, the distribution of this correlation is approximately Gaussian. So this is why we use Gaussian. Because the data that we are going to analyze, we use this transformation, then seems to work well. But we can, I mean, you can define the weighted stochastic block model the way that you want. You can put any kind of distribution here. Yeah?
If you think about this decision to call it the diagonal of 0, so in both models, so here it seems particularly weird because then you have, I mean, everything else is going to be some weird rational number, and then you're going to see exactly the
Would be, yeah, because there's no connection with.
in your community to see exactly what it is. In the other model, it's also weird because you want to have lots of connections inside your community.
Yeah, but I have no connection with the same edge. I mean, there are no self-loops. When I fix the diagonal equals to 0 only means that I don't have self-loops.
Sorry, in your B, you have non-zero diagonal.
Yes, yeah, yeah. Okay, so this is the only assumption. So if I collect the EEG data, there is no correlation between electrode with itself. So this is why we choose the diagonal of this matrix equals to 0. So the goal here is recover the communities, is do community detection for this kind of data, for networks that are generated from this model. So basically, we want to estimate C. So this is the goal here. Okay. So the methods that I study is always based on likelihood. So I write the likelihood of the model. That means I write the joint distribution of the data of W given the parameters. And then I'm going to look at this function as a function of the parameters. And what we usually do is maximizing this function on the parameters. Then I have the estimator for them, right? But what's the problem here when we use that? Is that when I write the likelihood, I just use the total probability theorem here. So I have the probability for the communities given pi, and here the probability to observe the random variables W given the communities, right? And then I need to sum over all possible communities assignments for the network. So this sum here make this likelihood not tractable to be computed. Okay, I cannot compute this value because this sum grows exponentially with n, so I cannot compute that. So work with likelihood here is tricky. So we don't, for community detection, there is no direct way to use likelihood as we are used to do. But what we have is that we can think this model as a mixer model because I have different communities, and inside communities I have different distributions. But the way that the way that we write the likelihood is not exactly a likelihood of a mixer model. And when we try to use methods, for example, there is a method in statistics called expectation maximization algorithm that we use when we have latent random variables, and when we want to estimate some parameters. We cannot use it here because in one step of this algorithm, I need to compute a probability that's not tractable because of this sum. So what we do sometimes is use a expectation maximization algorithm. We use a variational modification of this expectation maximization algorithm. So this is well known. So this paper here, they do that. They use a EM algorithm using this variational approximation of some probabilities. But the problem with the variational methods is that when the number of vertices in the network grows, it's very, very slow to compute the communities, right? But it works. So I put here the paper where they propose this method. But here they only propose the method. There is no theoretical results that this method really works. I mean, can estimate the communities. Well, okay. So what we propose here is my objective here is to use likelihood. Okay, I would like to use likelihood, but we know that I cannot use likelihood with these random variables W. Okay, so let me change the random variable that I'm going to write the likelihood. So now I'm going to define a new random variable. So the new random variable that I define here is this SIK. So let's see what's that. So suppose that I have here some labels of the nodes. So some community assignments of the nodes. It's not the true one. The true one, I'm saving the letter C. So C is always the true one. Here is any community assignment that I can do to the nodes of the network. Then what I'm going to compute here, I fixed node I, right? And I'm going to look at the sum of all edges of the vertices that belongs to community K that is connected to node I, right? So here I'm looking at all vertices that belongs to community K and is connected to node I, and I sum the strengths of this connection. Okay, this is a random variable because W is a random variable. So I can look at this new random variable here. So just to explain what I'm doing, I have this, I don't know, it was hard to explain, so I did this figure here. I suppose that I have only 5 nodes, right? So I have 5 nodes here. This is the true community. So node 1 belongs to community 1, node 2 belongs to community 2, and so on. And here is some labels, right? So the community 1, I associate, to node 1, I associated community 2. For the second node, associate now 2, and so on. Okay, it's just community any community assignment here that I would like to look at. So I fix here so I here is equals to 2 in this example here. And suppose that I fix here K, so equals to 2. I'm going to look all the strengths of nodes that belongs to community 2 that are connected to I. So what I need to do, I don't know if it's possible to see this gray entries here. I'm going to sum this one because the node here belongs to community 2. This one because the node here belongs to community 2, and the same thing here, right? But look at the true communities. We can see mismatches of these true communities assignments, right? So because of these mismatches, I'm summing here normal random variables with different means and different variances, right? But they are independent given C. So okay, they still independent, I'm summing them. Okay, I know this is Gaussian, right? At least. So let's see what we have here. So I define here a vector of all these S, so each one for each community 1, 2, and K. Given C, I know that this sum is independent, right? Because given C, the Gaussians are independent, and some different entries of the adjacency matrix, so the sum is independent. But one point here is that if I look the sums of different nodes, they are not independent. Why? Because remember that the matrix W is symmetric. So sometimes I'm summing the same entry. So they're not independent, but the independence is not too strong. It's just because of one entry, but still it's not independent, right? Okay, so I know that each S here is Gaussian. Let's see how is this Gaussian. So to see the mean and the variance of this Gaussian, I need to define here a confusion matrix. So confusion matrix is just a way to define, to describe the proportion of mismatches between two community assignments. So this is just the proportion of mismatches between the true and the community E that we assign. And now we can see that the sum will be a Gaussian with mean and variance that depends on these mismatches, right? Because since I'm doing this kind of combination of the entries in some wrong entries in some way, I have here now that the new mean and the new variance depends on this confusion matrix here. Right? So, but we know exactly how is this distribution. Okay, so now it's cool because I know that these variables given for each node I, they're independent. I know the distribution sense. Then I can write the joint distribution of Si just by this mixture here. And since given C, SR, all the entries are independent, I have this product here. So, okay, I can write this. And to write the likelihood of the model, I need to write the likelihood for S1, S2, and Sn, right? But I know that these random variables are not independent. They are not independent. But okay, the independence is weakly, so we are going to write what we call pseudo-likelihood. We are going to say, okay, let me forget that these variables are not independent. I will assume that they are, and then I can write the likelihood, right? Since I'm assuming that they are independent, I have a product here. This is the log. So I take the log, so it appears this sum here. And that part that we have before here just replaced with the Gaussian distribution. This is up a constant. I didn't write the constant here. And when we look at this expression, this is just a Gaussian mixture model. So using these variables as, I change my problem to a problem where now my likelihood looks like a likelihood of a Gaussian mixture model. And I know what to do with the Gaussian mixture model. In this case, I can use a expectation maximization algorithm, right? So I'm not going in details what this algorithm does. It's here. So what I do to estimate the community is just, I need to have an input. So I start with some configuration of the nodes. I need to give some community for each node of the graph, right? I start with this, and each time my algorithm will update some probabilities. So here I have a probability of node I belongs to community L, giving the data. This is this pi hat here. There's a formula to compute this, not put here. So I compute all these steps until convergence of the algorithm. And at the end, how I choose the communities. To choose the communities, I will choose the community for node I, that one that has the higher probability here to belong to that node, right? So this is how I will estimate the communities, and at the end, I will return C hat, that's the estimated communities of the graph. At the end here, I also have estimatives of the parameters as well. So I have the two problems at the end of this algorithm, right? Okay, so when I look at this algorithm, what's the problem is this one, right? I need to start the algorithm in such a way. It depends how I started. I can have a good estimation or not. This is the problem with this kind of algorithms. So the question is how the choice of this initial labeling, E, affects the estimator. Right? This is what we want to answer. So to answer this question, I need to do some assumptions here. I will assume that the initial labeling here matches a proportion gamma of the nodes of the two communities. Okay? I don't know which one. Doesn't matter which one. I just fix this gamma here, the proportion of nodes that matches between these two community assignments here. So I can define an error here, so the proportion of mismatches between the estimator that I propose and the two communities. What I want that this error here goes to 0. This is what I want. And then my estimator is really good. To have the theoretical results, we need to assume something more. So what we assume here is that all the variances are the same. I know this is a strong assumption, but it was hard to do without that. So we assume that all the variances are the same. And this is a very common assumption that we have, is that we have the same mean of the strengths of nodes that belongs to the same community. And we have the same mean for all nodes that belongs to different communities. Okay? So this is a way that I can write my model only with 2 parameters. This is done a lot in the literature. There are a lot of works doing this assumption. This is what we call homogeneous network. So this is what we assume. So what we prove here is that when we have a network, when all the pi's are equal to 1 over k, what that means? That means that all communities have approximately the same size, okay? So I have balanced communities. So I'm not in the unbalanced cases. So when all the communities have the same size, I can write the expectation of the mismatch of my estimator to the true communities. Just ignore the sub here. Just ignore a lot of it. This is just because I'm using an initial state here, so I need to look at all possible initial configuration for the parameter. So I'm just look at this expectation, the expected number of mismatches, the proportion of mismatches, and we have this upper bound for this number here that when you see here, it's going to 0 when the size of the network is going to infinity. So that means when I have large networks, I can recover the communities. Well, this is expected. And what's interesting here, we have the gamma here, right? The proportion of mismatches appears here, the number of communities appears here. But what's interesting is this term here. So what these terms tell me? So if I have the difference between the means that within community and between communities that are very close to each other, it's very difficult to recover communities, right? Because all the strengths of the network, the mean strengths of the network are barely the same. It's hard to recover communities. But when the means are distant, this difference grows, it's easier to recover the community, right? So we can see from this upper bound that happens. This is an intuition that we have, and we can see here, right? And what is interesting is that in this paper here, the authors proved an optimal rate of misclustering error for some kind of algorithms. And if you see the lower bound that they got here, it's exactly the same. We have the same part here in the upper bound. Let me just come back here. It's exactly the same. So up to a constant, we achieve the optimal rate of misclustering. Yeah.
What's so special with the value gamma? I guess the result is also.
I think it was just for, let me see.
Because here when gamma is equal to 1 over k, your right-hand side is just k minus 1.
Yeah. Yeah, it will be complicated. But it's just because of the computation that I did in the middle, but
You need to start with something non-trivial just to be good.
yeah.
You start with a random one, then it tells you basically.
Nothing, exactly. Because it's just a random way to assign it to communities, so it will be hard to detect them. Okay?
Does the other method, the previous method, work starting with half configuration?
Sorry, I'm sorry?
So the other method, this one,
Uh-huh.
does that one work from an arbitrary
No, they prove this upper bound for any method. I don't know exactly if they have or not. Yeah, it's the other direction, exactly. But they also they propose a method in this paper, but it's based on spectral cluster, so doesn't assume any initial labeling, that achieve this upper bound. I use their method. I'm going to show in the simulation. Okay, so this we also can have the means and the variance growing with n, so it can depend on n. And then if that holds, we still have consistency of the method. And for the unbalanced case, we also have a result, but it's too ugly to show the formulas. But basically, what we have is that under this assumption, we can recover the communities as well, right? So we have for a balanced and for an unbalanced case. Okay, let's see some simulations in the application, then I finished the talk. So here, what I did here is just think about a community, a network with 3 communities. So I have this matrix of means. So I have mu1 in the diagonal because I'm assuming that within a community I have the same mean, and between communities I have the same mean, me2. The variance is fixed. And what I plot here is the difference of the means that we saw in the theoretical result that if the difference grows, it's easier to recover the community, right? And here what we have is the proportion of mismatches of the estimator with the true communities. So if it's going close to 0, that means that's really good. So here we compare different methods. So the purple one, PL, is just our method when I just flip. I think I just flip like 7% of the communities. So I know the true one. I just change 70%, and then I start the algorithm with that. Of course, we are not doing this in real life, but just to see that, of course, it works well, right? Because I know gamma is 0.7. But okay, so this is purple line, doesn't match much. And the orange or yellow line here, I apply spectral clusters, the same method that they use for binary, I just apply for weighted networks. So I apply spectral cluster here, is the yellow line, and then in green line, I use the result of a spectral cluster, has the initial communities of my algorithm, and then I apply them. And then you can see that I improve here spectral cluster because the line of the PL spectral cluster is below of spectral cluster. So we can do this to improve some methods, right? This B is the method that they propose in this work here that achieves this optimal rate. Their method is the red line, and here I do the same thing. I use the pseudo-likelihood algorithm using the result of their method has the initial value, right? So what I have here is balanced communities. Here's just change n. Of course, when n grows, it's easier to recover community because I have more data. So, right? So in statistics, it's what we have. But here I have unbalanced case. Here is the unbalanced case. So I have pi. Here is not 1 over k. So I have unbalanced communities. And we have the same thing. So PL is always improving the other methods. So what we can do in real life is using some method to infer the communities and then apply the pseudo-likelihood algorithm, right? Because we need to have an initial configuration. So just to finish, I would like to talk about some application. So here we have data from fMRI of 54 schizophrenic patients and 69 health patients. So it's resting fMRI, so they just collect the information of their brain. Here I have a network with 264 nodes. And we apply what I explained before, this Fisher transformation of the correlations, and then I have a weighted matrix, let's say, a matrix with continuous entries, and then so I have a weighted network, right? And I use this weighted network. But the point here is that I have a kind of sample of populations, and our method, which you only have one network, right? So what we do here is kind to compute some average of these 54 networks to have only one network for the schizophrenic patients and one network for the healthy ones. So I only have two networks. I would like to compare the community of them. What we have in fMRI, there's this power parcellation. That's a way that they divided the nodes of the graph of the regions of the brain. And they know, for example, the P1 region, there are third nodes that's related with sensory-motor hands. And they have these 14 ways to divide the brain. So what we do is, okay, since there are 14 communities here, right? I'm going to define that K is equal to 14, and then I use our method to estimate the communities. So what I did is just apply spectral cluster, and then with the result, use as initial state of our method, and then apply our method to estimate the communities. So, okay, what we have here. Let's look first in this picture here. In this side, I have the communities estimated for the health network, right? So H1 is the first community estimated for the health network, and so on. And here I have this way that they divided communities according to this power parcellation, right? So what we can see here is that, for example, H1, a lot of nodes of H1 belongs to this power parcellation here. And we just have a few that belongs to this one and this one, right? So this is just a way to compare the communities that we got here with the power parcellations. That's kind of defined by the neuroscientists. But what we want to do actually is compare the healthy with the schizophrenic network. So we did that in this way here, and we can see that many communities, they're kind of stable, right? For example, the H community for the health overlaps a lot, the H community of the schizophrenic network, so they're kind of stable. But what's interesting here is that the second, this one, you can see that it splits a lot, right? There's a lot of different matches of the nodes here. And let me see, H11 is the same. And when you go back to this picture here, we see that H2 concentrated the nodes in this P5 power parcellation, H11 2, right? We can see here a lot of nodes that overlap with this P7 power parcellation. If you go back here, P7 is related with the full mode. That is known in the literature that's correlated with schizophrenia and other disorders.
Can you show us that plot again?
Sure.
Yeah, so these are different things, right? So one is just a healthy brain, or kind of average healthy brain.
Yeah.
Connection
Here, health and schizophrenic.
And here comparing healthy versus schizophrenia.
Yeah.
And then you're trying to see if there's a difference. And what you're saying is that you're taking the difference that you see on the right-hand side.
Mm-hmm.
Then you look at the left-hand side, that corresponds
To P5, yeah.
Misplaced connections in P5 or something like that.
Exactly. This is what we can see. I mean, it's difficult to analyze because we don't have grand truth in this case, right? We don't know the true communities, but we try in some way to interpret the communities that we got. So this is one nice result because they apply also different community detection methods for this data, and they detect exactly the same thing, that is connect the difference that we have between health and schizophrenia is related with this default mode, with this P5. So it's kind of nice. I mean, we got something that is related to what they found before.
So can I ask one more question?
Sure.
How variable would be these plots for healthy and schizophrenic
Yeah, probably very different, but I didn't try to test different for each patient, yeah.
Right, but the communities you think are stable?
It's an assumption, yeah. Okay, so just some final remarks here. As I said before, we use this assumption of homogeneous models, right? Because I assume that I have the same mean within communities and the same mean between communities. I mean, from the theoretical point of view, but the algorithm works well if I have a heterogeneous network, but still, if we want to have some properties of the estimator, you need to investigate it theoretically what happens in heterogeneous networks. And one thing that would be interesting is to write a model that incorporates distributions with a point mass at 0. Because what happens here is the way that I define the model, 0 means there is a connection, but the strength is 0, is null, something like that. So what we can try to do is use a different distribution, for example, first to see if there is a connection or not, and then if there is a connection, you give the strength of that connection. So this is something that a student of mine, my master student, is doing. We are using this distribution that is known in statistics as zero inflated distribution, because they model distributions that have a lot of zeros. For example, if we use a Poisson distribution, you have a probability to observe 0. But if you have a large parameter, the probability is small. So you can do, for example, you can mixture a Poisson distribution with mean that's very high, but that can generate a lot of 0 as well. This is the inflated models. And we are using that to describe the airport network, because in the airport network, we are modeling number of flights. So we have a discrete age. So we are trying to do this kind of edges distribution to define a model and then recover communities. But what we are doing, we are applying these variational methods that I said before. It's this variational EM algorithm to recover the communities. But this is still an open question if you want to model a lot of zeros and continuous distribution, continuous weights. So that's all. Thank you.
So we have some time for questions from the audience.
Your mean density inside is larger than outside, then if you with hypermobility every vertex, you're just looking for a min cut.
Mm-hmm.
So why is this method better than just being greedy, like moving vertices one by one to maximize to minimize the cut? I mean, I'm thinking with two classes.
Okay. Mm-hmm. I don't know if I understand exactly what you mean. So
just as two classes.
okay.
Take any old country, and they say, okay, I'm going to look for a vertex. It's got more neighbors in its own side and the other side, and it stays. It's got more neighbors the other side, move it over. Just keep moving vertices one by one. Every time you decrease the cut, and after some steps, then you have it. That wouldn't work in more complicated settings. But
I see.
Probably
I-
have to do the one vertex on one vertex.
right.
Yeah,
So
you have,
want a
yeah, that's
balanced
what
cut.
it's a balance cut, so it's different. And then it's NP complete and altered.
Yeah.
Yeah, I mean, if you just look at the combinatorial problem.
Right. If you want to actually minimize it, then it's.
Yeah, if it's a minimum balance cut, it's different from min cut, yeah.
I see. But can you approximate in monoreal time?
I think
Don't
the
know.
answer is yes, but then the people who, yeah, I mean, the people who do very fine analysis of these things, right? And then the approximation is going to give you an error factor, right? And you can do better by looking at these no backtracking.
I see there's no backtracking thing a lot.
I mean, I've seen it also. I'm not sure I understand it completely, but so I can take what I'm saying with a grain of salt.
So you assume that the size of the number of clusters does not grow.
Exactly. Yes.
But you still have consistency if k is
Grows. I don't. I have a problem with k here, right? But of course, I can look at this and try to see the.
exponential of
Yeah. So I need to.
k is like square root of n.
Mm-hmm.
Exponential. I don't know. I think those things goes to 0 if
Yeah, I mean, we need to put some to see what's the condition here. Yeah, you are right. I never tried to do that, but I know that there are some models that they construct the kind of stochastic block model in such a way that the number of communities grow. What they do is just use the Chinese restaurant process to assign the communities. And what's nice, because I'm working on that, and when you observe a network that have a finite number of community, this method cannot estimate well the number of communities because they always estimate more communities than what you really have.
my second question. I think that your algorithm is O of n if you assume that each iteration of the expectation simulation is O of n if you assume that k is constant, right?
Yes.
But if k is not constant, for instance, if k has the order of n,
Mm-hmm.
that would be something like O of n.
Yeah, you need to deal.
Something like that.
Yeah, there is an algorithm that does that. I think it's the reversible jump. I don't know. They use this reversible jump when you have this, that the complexity of the model change of each step of the algorithm. I have seen this on networks, but I didn't see clearly what they do. But I think there's.
So, you were trying to avoid confusion log-like,
Exactly.
right? And you have a way to avoid that.
Yes.
Context where k is small.
Yeah.
Okay. My question is the following: couldn't you avoid that just by like sampling some paths in your graph and then maximizing the likelihood on those paths? For instance, I can sample 100 paths.
I see. Mm-hmm.
Graph of size 100.
Mm-hmm.
Okay, and I can estimate the log likelihood of those graphs.
I don't know if 100 is. I think for 100 is still not. It's not trackable to compute. But I mean, I got it. Yeah, I think it's probably a way. I never have seen this before, but
But my question is,
sounds yeah.
how to sample those paths in a way that they are representative?
I see. That's a good question. I mean, there are people working on problems in how to sample data from networks, but I've never worked with this before. I don't know exactly, but I can assure that there are people look at that. So that's interesting. So, thank you. You.
I back in the time when I knew more about this, I still know, but it kept with the times with community detection. But I remember there were like two algorithms that were kind of nice. So one was spectral clustering, which had this cool thing that was finite in time, like it was polynomial, right? Because just calculating eigenvectors. But there was also this AMP that people like were also interested in.
What's the name again? I don't.
AMP, so approximate message passing.
I don't know this one.
You keep like in each vertex, you have this idea of like of what is the community of each vertex, and then you keep sending messages back and forth, and then non-backtracking thing that then started being used in the spectral filtering. So the idea of the backtracking came a little bit from that. And so my question is, have you thought about it, like AMP for, because I think AMP might be robust to these different communities, like different means and covariance.
I see. I never have seen this one, so I'm not familiar with them. About spectral cluster, one thing that happens is that when we have unbalanced community, sometimes spectral cluster doesn't work well because we have communities of different sizes, but they have some corrections that you do, you project. I mean, you do some correction there and then you can recover, but that happens sometimes with spectral cluster. So.
So this upper bound is the lower bound from that, right? The minimax lower bound. So these are, I mean, the kind of argument that you use to prove these things, is it kind of like Kuiper-Kleiber related entropy kind of argument?
Yes, actually the result is established with the Rényi divergence here. I just used the Rényi divergence for Gaussian random variables. So actually, to be fair, the result that they prove is for any kind of distribution that you have for the weights. I mean, under some assumptions, and that depends on the Rényi divergence of this distribution within and between the communities.
Right. So, yeah. So and then, but the upper bound, I guess, the proof is probably different. Right?
Yeah. This is different. We just look point by point, try to make it optimal. Yeah.
So, more questions, comments? Well, if not, let's thank our speaker. And,
Thank you.